This homework is revising everything that we've learned about binary and 2's complement. So, first question's very straightforward, just a bit of practice on binary notation. So remember, we write down our pattern and sequence, remember, which was 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on, to give us those combinations of numbers at the top. And hopefully these ones, we've done them so many times that we just write the specific numbers underneath them, and we add up the places that have the numbers below them, so we get 108 as a total for this example here. So that way is reasonably straightforward. Whenever we do the opposite way around, I like to think of filling a gap in a wall. So if we had a wall size 66, and these are the different numbers of bricks we could order, we place zeros where they're too big and a 1 where we can order it. So if we order 64 bricks, that would leave us with a remaining gap of 2. So the 32 would have to order 0, the 16 0, the 8 0, the 4 0, the 2 would have 1, which would leave 0 of a gap and no more. So this number would give us 66. So those ones are very straightforward with us. 2's complement is where it starts to get a little bit trickier for us. So I'll try and write this a bit more space. 16, 32, 64, 128. Now remember, the quick shortcut cheat is that if we put negative 128 at the front, we can quickly test our working, but we also need to demonstrate the correct way of changing a number from decimal to binary. So if I just choose a random number here, and we need to remember what the process is. So the first step is to invert all the zeros into ones and the ones to zeros. Now I only do this because the most significant bit is a 1. Now in 2's complement, that indicates a negative number. The same with signed bit notation. If that was a 0, I wouldn't actually do this step at all. So after inverting, we have 0, 1, 0, 0, 1, 1, 0, 0. And the last step is to add 1 over here, so plus 1. And we need to know the different rules of addition. So 0 plus 1 gives us 1 with no carryover, which means we basically just write the rest of the number down as we find it. And like we did in the previous part, we just add up all the numbers that correspond with the 1. So we get 64 plus an 8 and a 4, which is going to give us 76. And this is where people forget that the whole purpose of doing the inverting and adding 1 was because the numbers are actually negative. So don't forget to write down that your final number is actually a negative, otherwise we wouldn't have done that whole process in the first place. So be very careful, and a 2's complement number 0 at the beginning is a positive number, so you don't have to invert and add 1. To do the opposite way, so for example, if we want to represent negative 40, so 1, 2, 4, 8, 16, 32, 64, 128. And I'll use the cheat to check my answer this time. So the first thing we've got to do is write down what 40 is in binary, just positive 40, which is very straightforward. And we actually carry out the exact same process, which is why 2's complement's really neat. So we add 1, 1, 0, 1, 0, 1, 1, 1. And the next step to add 1. Now this is a slightly trickier binary addition. 1 plus 1 is actually 2, or a 1, 0 for us, but the 1 carries over. Same again, 1 plus 1 is 2 in binary, or 1, 0, so the 1 carries over. 1 plus 1 is 2, so the 1, 0 carries over. 0 plus 1 is 1, and there's no more carryover, so we can just write down the number as it was before. So this number here, this binary number, is the representation for negative 40. And if we were to do some quick maths by doing -128 plus 64 plus 16 plus 8, hopefully you would know that that gives us -40. It's a quick way to test that you've done it correctly, and if it didn't match up, then you've obviously made a mistake at some point, so it would be a good idea to go back and check that. Next question is all about how to carry out an arithmetic shift. Now we can either shift left or right. So if we shift numbers to the right, that has the impact of dividing a number by 2. Shifting left has the impact of multiplying by 2. Now to carry out an arithmetic shift, try to remember that A is the first letter of the alphabet, and remember that the most significant bit is preserved. And if you do some different calculation practices, you'll realise that if you didn't preserve the most significant bit with arithmetic shifts, i.e. 2's complement representation, which is what arithmetic shift suits, it would completely mess up the numbers. It would flip the signed bit for some of them, and make positive numbers divided by 2 would suddenly become negative and vice versa. Logical shift is where the most significant bit is not preserved, so this is not good for negative numbers. So we would never use it for 2's complement numbers, otherwise it wouldn't work at all. So the A shift, the arithmetic shift, is when we have 2's complement numbers to preserve the sign and you save the most significant bit. And the logical shift, left and right again, has the same impact of multiplying by 2 and dividing by 2. It's just that we don't preserve the most significant bits. And that should help answer the difference between arithmetic and logical shifts. 2 disadvantages of signed bit notation. I'm going to get you to do some research. However, I will put this as a quick indication of one of them, and this is another hint at the other one. So use your notes, use the forum, use the textbook to try and find that answer if it's not something you remember.